For example 2, find the value of the derivative at each indicated value. So the first one, I've got y is equal to 9 times x squared minus 3, all of this divided by x to the third. We want to find what is the value of the derivative specifically at 3, 2. So do I need to use the quotient rule on this? Why don't I write with the scissors tool? Okay, that makes sense. Quotient rule? Question mark? I'm going to say, I think I can get away with not having to do that. I just got to rewrite it. So if I distribute the 9 through here, 9x squared minus 27, I'm going to divide both of them by x to the third, and I would have 9x to the negative 1 power, and minus, not plus, minus 27x to the negative 3 power. All right, then I don't have to use the quotient rule on it. It might save me a little bit of time. So y prime is equal to, leapfrog that thing down, negative 9, x to the negative 2 power, and then leapfrog our power down, that'd be 81. So plus 81 x to the negative 4 power. And then I don't like to have negative exponents, so let's pull out something. Let's pull out the lowest exponent, which of course is going to be our x to the negative 4 here. So x to the negative 4, divide both of these things by x to the negative 4. So we're going to have a negative 9 x to the, let's see, I have x to the negative 2 divided by x to the negative 4. You subtract your exponents, negative 2 minus a negative 4 makes positive 2. And then plus 81, right? And then I might just bring that down to the bottom of the fraction to get negative 9x squared plus 81. And yeah, you could have, if you wanted to, you could have pulled out, say, a negative 9 from that as well. Yeah, let's see. And then put this over x to the 4th. There we go. So there's y prime. And maybe I just go ahead and factor the top two, just because it might make it a little bit easier for us to plug in 3 there. Actually, no, it wouldn't, because watch. Y prime of 3 is equal to negative 9 times 3 squared plus 81 over 3 to the 4th. Okay, so our 3 squared is 9. 9 times 9 is 81. This is negative 81 plus positive 81. I get 0 on the top. And I don't have a 0 on the bottom because that's a positive number, so this whole thing is equal to 0. So the value of the derivative at this particular point, whole lot of work just to get 0. I wonder why. Okay, let's take a look at number 2. What is the value of the derivative of y is equal to the absolute value of x at 0, 0 at the origin? Well, we don't have a derivative rule for the absolute value function, so instead, maybe what I do is I just examine a graph here. Voila, there's our x and our y axis, and then the absolute value function looks exactly like this. And what's the value of the derivative right here at this point at the origin? Here, y prime does not exist because we have a sharp turn. Okay, and now notice on this particular graph that this is, that's the absolute minimum point on this graph, was right there at that sharp turn. I wonder if something similar is going to happen over here in number 1. I don't know. We'll have to look at a graph later. Okay, and then finally on the second number 2, this is the way you count in calculus, 1, 2, 2. Anyway, we've got y is equal to the sine of x, and we want to find the value of the derivative at each one of these 2 points, pi over 2 and 3 pi over 2. Okay, what's the derivative of sine? That's easy. It's cosine. And now let's find, whoops, that should be a prime, y prime of pi over 2. So that's the cosine of pi over 2. Draw a little unit circle here. Pi over 2 is right there. And the value of the x-coordinate there would be 0. You seen a common theme here? So y prime of 3 pi over 2. Cosine of 3 pi over 2. So 3 pi over 2, this time it's going to occur down here. And again, the x-coordinate for cosine is going to be at 0. Where do these points occur on the graph? Well, here, let's take a look. Let's go back over here to this nicely animated PowerPoint slide. So here's the first one. And we found the value of the derivative right here at x equals 3. We found it to be 0. And you can see for the graph that we have a relative maximum value. That's right there. Okay, and then we also looked at the absolute value. And then right here at the turning point, which is the sharp turn, we had an absolute minimum. And it occurred where the derivative did not exist. Then over here on the sine graph, let's draw a little sine graph, we had a value of the derivative being 0 here at pi over 2, a value of the derivative being 0 at 3 pi over 2, and we have a relative maximum and a relative minimum. So these are critical numbers for this graph. We're calling these things critical values. And this is going to be the first step that we take in order to find our extrema, our relative mins and maxes. We're going to start by finding the critical values. How do I do this? So this example was kind of trying to model that situation. You're going to take your function, you're going to find its derivative, and you're going to set that derivative equal to 0 or find where it's undefined. And that's where these minimum and maximum values could potentially occur. Okay, so let's define critical numbers. Let f be defined at c. So our function is actually defined at this x value, c. If f prime of c is equal to 0, or if f is not differentiable at c, then c is called a critical number of our function f. So here, f prime of c, whatever the c value is equal to 0, get a horizontal tangent line, and notice that we care about that particular point because that's where we could have a relative minimum or maximum point. And then on this next picture, we have ourselves a value of the function where the function's derivative is not defined. We get a sharp turn, but at that sharp turn, we have a maximum value. And that's, again, why we care about these things. So this brings us to Fermat's theorem. It's not Fermat's last theorem, if you're familiar with that. It's just one of his multiple theorems. Fermat's theorem, it has to do with these extreme values. It's often referred to as just simply extreme values occur only at critical numbers. So, in other words, if f has a relative minimum or relative maximum at x equals c, then c is a critical number of f of x. So this is where the derivative is either equal to 0 or where the derivative is undefined. That's to be a critical number. So notice that the order of this statement goes, first, we have to have a relative minimum or a maximum. Then we can conclude that that is a critical number. Does it work in converse? If I flip this thing around, does it still work? And that's what we're going to try to figure out in the next video.